Come with me as we conclude our three-part series on circle theorems that will involve some algebraic proofs. Today, we're diving into some circle theorems proof, a very important topic, particularly if you are preparing for your GCSEs or any external exam. We'll go through the final three theorems, including one that students find very tricky, the alternate segment theorem. I'll break down each proof question clearly with simple diagrams and easy tips to remember. By the end of this lesson, you'll feel so much more confident to tackle any circle theorems question that come your way. So, grab a pen and let's get started. In our previous lessons on circle theorems, we have looked at the following. So just a quick recap before we come down to doing the final theorems and also our proofs. So, in our first lesson, we looked at angles in a semicircle is equal to 90 degrees. We also looked at angle at the center is twice the angle at the circumference. We looked at radius and a tangent meet at 90 degrees. In part 2, we've looked at opposite angles in a cyclic quadrilateral add to 180 degrees. We also looked on the fact that two radii create an isosceles triangle. And the final concept we looked at was a tangent that's drawn, two tangents drawn from the same point will be equal in length. Now we're going to just summarize this series by looking at the final few theorems, and then we'll get into some circle theorems proof, which is of 4 and 5 more questions. So, rule number 7. Angle in the opposite or alternate segment is equal. So the angle between the tangent and a chord is equal to the opposite angle in the triangle in the other segment. And this one is said to be the most difficult theorem to remember. So let's now visualize that diagrammatically. So here I've got a circle. Now if I've drawn this triangle in and I make a tangent, now the angle between the segment here and the tangent is equal to the opposite one in the triangle on the other side. So I can see color coded here, A would be equal to the angle on the outside between the tangent and the chord, and B in the triangle will be equal to the angle here between the tangent and the chord. And remember, always we talk about different orientations we could have. So here in numerical context, we have 44 to be the angle between the tangent and the chord, and that's also 44 for the angle on the opposite side of the triangle. And then just another orientation here, we've got 66 in the triangle, and the one between the chord and the tangent will also be 66 degrees. So now we're just going to do 2 questions to practice that theorem. So example number 1. We're asked here to find the value of the angle marked A, B, and C, and to give reasons for our answer. Now we think first of all, we need to use the theorem that we've just learned. So angles in the alternate segment are equal. So therefore, I can simply write down from the diagram the value of A and B using this theorem. So I can see here from my diagram that angle A is the matching one for 77 because the angle between the chord here and the tangent will be equal to the opposite one in the triangle. So therefore we can write that A is equal to 77 degrees as well, and I've already written the reason here. B then would be equal to 71 degrees, just to put a double line here to give a focus. So B would be equal to 71 degrees for the same reason. Now, a good practice is to put in that on the diagram to close the gaps. So we said B was 71 and A was 77. So we put that in. Now we're just going to go to our next step, which is angles on a straight line we know add to 180 degrees. So we're going to form an equation to find the value of C. So we can see here, if I write 77 add 71 plus C should give us 180 degrees. So we're just going to add these two together and subtract that. I'm just going to do that quickly on the calculator, just to avoid any error at this stage. So 77 plus 71 gives us 148 plus C equal 180. Final step, C then will be equal to 180 degrees, take away 148. And the answer is C will then be 32 degrees. And there we have our first question on the angle in the opposite segment or alternate segment theorem. These things can be so tongue twisted sometimes, but let's go. All right, for our next question, we are given example number 2. We're asked to find the angle marked X and give a reason for our answer. So again, we observe our diagram and we look for the reasons that we need to use to break through in this question. I can see here that I can enforce my rule that I've just learned. So I need to find X, but we know that we need at least 2 angles in a triangle in order to find a missing angle. So I can use that theorem, angles in the alternate segments are equal, and I can just write that on the diagram here. So this angle here will also be 64 degrees. Now I have enough information to find the missing angle. So step 2, angles in a triangle again add to 180 degrees. Therefore, 64 degrees plus 43 degrees plus X should be equal to 180 degrees. And we just put that in our calculator again, adding those two together. We get 64 plus 43, and that's equal to 107 plus X gives us 180 degrees. So we need to subtract 107 from 180. So 180 take away 107 degrees, and that gives us 73. So X then is equal to 73 degrees. And there we have done 2 questions just to embed that concept. So we're going to move on to our next theorem, which is rule number 8. So rule number 8 says angle in the same segment are equal. So another one that sometimes is very tricky as well. Now, all triangles drawn from a chord will have the same angle where they touch the circle. Also, the 2 angles on the opposite side of the chord will add to 180, and this brings us back to the cyclic quadrilateral we've dealt with in previous lessons. So visualizing this, if I have a chord here and I draw a triangle from that chord and I make another triangle from the same chord, very important there, it has to be of the same chord. When this happens, the 2 angles in the triangle touching the circumference will be the same, and that's because they are in the same segment drawn off the same chord. And I could make another diagram here just to show different orientation. So I've got a triangle there from that chord and I make another triangle from the same chord. It means then that those 2 angles will also be the same. Now, a very tricky part here is that not every diagram comes with the chord being drawn for you. Sometimes you have to put that chord in for yourself to see that theorem in action. So now we're going to do an example to practice this. So example number 1, we are asked to find the value of the angle marked X and also give a reason for our answer. Now, I've always said, even if the question doesn't say give a reason for your answer, you also need to do that just in case hidden marks are given for the reason. And also it does help you to practice your theorems as well in terms of the reasons. So looking at this question here, I can see a very good example of what I just said, that not always the chord is visible. So if I look here, I can put my chord in for myself, and then it is now clear that I've got these two triangles drawn from the chord, and I'm asked to find the angle X. Now, what is my first step? Now, I can see I do not know an angle in the triangle. However, I know an angle that links to one of them in the triangle. So here, I'm just going to fill this in and call it Y. I can see now my first reason would be angles on a straight line add to 180 degrees. So therefore, I can find Y. So Y plus 128 degrees should be equal to 180. So we're going to need to subtract 180 from both sides here, 128 from both sides. So we put that in our calculator. On this side we get Y. So we just need to do 180 take away 128. And that gives us 52 degrees. So Y is 52 degrees, but I wasn't asked to find Y. Clearly, there's not much work to do here because I'm now going to use my theorem that I've just learned. Angle in the same segments are equal, so that's my second reason. And therefore, if Y is 52 degrees, then X would also be equal to 52 degrees because angles in the same segment are equal. And just like that. So we're always looking for angular connections. Angles on a straight line, angles around a point, and any theorem that we've learned, we may need to use that to fill in the gaps. That will help us to close in on the answer we're asked to find. Well done for making it this far. So we are now going to look at a second example on that rule. So we are asked here to find the value of the shaded angle and also give reasons for our answer. Now, if we take a look at the diagram here, we can see we were explicitly given the center of the circle. Therefore, the line passing through the center of the circle is clearly a diameter. Now, in the previous example, I did say we have to take opportunities. So I have to link this with something I've learned before, one of the theorems. So our first step to unlocking this question is to use the skill angle in a semicircle equal 90 degrees. And for this, I can just write this on the diagram. I know if I have an angle formed of the ends of the diameter of a circle, the angle where they meet will be 90 degrees. So therefore, this angle is 90 degrees, which I can fill in. Now, focusing on just the triangle here, I know 77 degrees and I also know 90. That means I can find the angle here, which is the breakthrough I'm looking for. Because I've got the segment here and this angle here is in the triangle that's coming off that chord, and also the one I'm asked to find comes off the same chord, which means that our second reason will be the angle in the same segment are equal. But before we can do that, we need to find the missing angle here, which I'm just going to call X. So I'm going for angles in a triangle add to 180 degrees. So I know 90 degrees plus 77 plus x should be equal to 180 degrees. Now, because I know that this angle is 90, it means that 77 plus x should also be 90. So I didn't have to go all that long route. I could just use 90 as well, just to make that little note there. But since I've written this equation already, I'm just going to use the entire thing. So we just need to add 90 plus 77. That gets us to 167 degrees plus x equal 180 degrees. Now I need to subtract 167 from both sides, and then I would have found x. So 180 take away 167 is 13 degrees. So I put that on my diagram, and I can see here, having found x makes me also find the one I was asked to find using angles in the same segment are equal. So then I write the shaded angle is equal to 13 degrees. Very clear logical steps there. So now we've practiced 2 questions on that theorem. We now go on to look at the perpendicular chord bisector is a diameter, and that's the final one before we get into some circle theorems proof. So, important note here, no matter where you draw the chord, the line that cuts it exactly in half at 90 degrees will go through the center of the circle, and that is the diameter line. So we look at that. Now I've got this chord here. Once I have a line passing through the center, cutting this line, it will be perpendicular, and therefore a 90-degree angle is formed. And I'm just doing this one on the same diagram, just doing some animation there. The orientation doesn't matter, so it could have been oriented this way as well, and also going around again could be that way, could also be that way. Okay, remember I did say in previous lessons, do not be afraid to turn your paper so you can see what's going on. So I could also have a chord there and make another diameter going to the center there. Another 90 degree is formed. So this one is usually very, very simple. And we'll just do one question to show that. Now, here we are given this example and we are asked to find A. Clearly, we can see that we've got a 90-degree angle because these two lines are perpendicular. Therefore, we know the angle in a triangle at 180 degrees, but if this is 90 degrees, we could also assume, or we know, not assumption, we know that A plus the other angle 54 will also be 90 degrees. So I'll take that route this time, a very shorter one. So then I'm just going to write that A plus 54 has to be equal to 90 degrees. So A then will be equal to 90 take away 54. So I'm just putting that in my calculator as well. So I'm just going to do 90 take away 54, and that gives me 36. So A is equal to 36 degrees. Very, very simple one there. So I won't have to do another example. We just know once two lines are perpendicular, the angle formed is 90 degrees. Okay, now having done all of that, we're going to the back of the paper. When you are doing your exam, towards the back of the paper, there are usually the circle theorems proof, which lots of students tend to just leave that one, say, oh, that's not for me. But we have come to a point where we recognize through the lessons we've done so far, once we have that clear logical thought, we can tackle any question at all. So we're going to look at a few 4 and 5 marks question now that ask us to prove these theorems. And we know that once we talk about proving, it is always algebraic. So let's go to our first 4 marks question. We're asked here, and the language confirms what I'm just saying in this question. It says, prove algebraically that the angles in a semicircle add to 90 degrees. Now, we've done previous lessons where we looked and do example of questions here, but now we're asked to prove that this theorem is actually true. So I'm going to go step by step here, nice and smooth, so that you understand clearly what to do. And I will suggest you draw this out and work along so you can visualize what we are doing. So step 1, we need to draw a radius to meet the circle at C. So I'm going to put that line in. So that's the first step. Now our second step, we need to label the base angles in both of the isosceles triangle that's formed in terms of X and Y. So just to reiterate, once you have a triangle, 2 radii, we explored that theorem, create an isosceles triangle. So triangle OAC is isosceles, and also triangle OCB. So I'm going to call the angle at the base here X, which means that this angle will also be X. And then I'm going to call the one here Y, which means the other one will also be Y. So we've put that in. Now we need to find the sum of the angles in the triangle in terms of X and Y. So if you look here, we've got X add X, add Y, add Y. So, and that's equal to 180 degrees because the angles in a triangle add to 180. Remember, we are after proving that the angle at C is 90 degrees. So let's see. X plus X gives us 2X, and Y plus Y gives us 2Y, and that's equal to 180 degrees. Now, if we divide this by 2, we're going to get X plus, so 2x divided by 2 is x, and 2x divided by 2 is y, and 180 divided by 2 is 90. And we can see here that at C, the angle here is x add y. So we have proven that x plus y is 90 degrees, which means the angle in a semicircle is equal to 90 degrees. And just like that, we've proven it algebraically. Beautiful. Now, once you have gotten this idea, the same principle applies to any other proof question. And also, we will be relying on our skills in terms of different angle properties as well. So 4 marks that you would have normally left, it's really that simple. Okay, so we're going to go into another proof question. We're asked here to prove algebraically that the angle at the center is twice the angle at the circumference. Another theorem we've dealt with before. This one, however, is 5 marks. Indication here, we've got more things that we're going to need to do. So, step 1. We're going to do like we did in the previous question. We're going to start off by drawing a radius to meet the circle at A. So we put that in. Now, once we've done that, I think you know where this is going, similarly to what we have done before. So step 2, we're going to label the base angles in both isosceles triangle, X and Y. So I've just pre-done that one there, since we have done the other one from scratch together. If you put your angle there, call that one X. Put the other one isosceles, so it will also be X. Then for the other triangle, we call those X and we call those Y. Beautiful. So what we are trying to prove here is that the angle at A will be 2 times the one at the circumference. So let's see. So then so this one here, just to point to it quickly, it should be twice as much as the one at A. So next step, we need to find the unknown angles in both triangles, okay, in terms of X and Y. So I can reason here that if I have X and X, that's 2X, and we know the angles in a triangle are to 180. So the angle here then has to be 180, take away X plus X, which is 2X. So I'm just going to write that here, 180 minus 2X. And you can reason that the other angle here would be 180 minus 2y. 180 minus 2y. So I'm just going to write that here. 180 take away 2y. Okay, for our next step, we simply need to find the angle at the center now in terms of x and y. And we know that the angles around a point add to 360 degrees. So therefore, the angle here at COB would be equal to 360 degrees. Take away the sum of the other two angles. I'm going to put that in bracket. It's very important that we put that in bracket. So it's 180 minus 2x, and we're adding that to 180 plus, minus 2y there. We're going to simplify the bracket first and then expand it. So it's going to be 360 take away 180 plus 180 in bracket is 360. And then we will have minus 2x and minus 2y. We then use the negative on the outside of the bracket to expand the bracket. So we've got 360 minus, indicating minus 1 times by 360 is minus 360. Negative times negative is giving us positive 2x. And negative times negative here will give us positive, which is positive 2y. We can see here that 360 take away 360 is equal to 0. So all we have left for the angle at the center is 2x plus 2y. I write that in. 2x add 2y. Now remember, we are asked to prove that the angle at the center is double the one on the circumference, and the one on the circumference is at A is x plus y. So therefore, if I factorize this, taking 2 out as my common factor, I can see here that multiplying x plus y by 2 gets me to 2x plus 2y. So therefore, I have proven that the angle at the center is twice the one on the circumference. 5 marks. 5 marks is a big marker to up your grade. And so then, I am so happy that you are now able to do this. Awesome. Now, before we get into our next question, just checking, did you remember to subscribe? Have you shared? Have you hit the notification bell? Have you liked the video? And also, make sure that you comment in the comment section. Let me know that these have been helpful for you. Also, remember, we are on TikTok, and I'm going to be doing some more proof questions over there so that you have those on the go as well. So remember, follow us there as well. So now we're going to go into our next question. P, Q, R, and S are points on a circle. We look and we identify those points. Great. PXR and QXS are straight lines. PX is equal to SX. So PX is equal to SX. We can see that those are on the triangle, and we're told it's not drawn accurately. We're asked to prove that QS is not a diameter of the circle. 4 marks. So we already have a thought. We know based on the question it is not a diameter, but we have to prove this. Now we look and see what are some properties we've got that we know that we can employ to this question. Now the fact that we're told that PX and SX are equal on this triangle, we know the triangle is an isosceles triangle. So we're proving, we want to know if this is 90 degrees. If this angle is 90, then we would have known that this is a diameter. So clearly we are proving that that angle is not 90. So I know that the angles in a triangle add to 180 degrees. So I'm just going to call the angle here Y. So we know this angle here would also be Y. So I can find out what Y is by 2y plus 50 should be equal to 180 degrees. So if I subtract 50 from both sides, I get that 2y is equal to 130 degrees. Then all I need to do is to divide by 2 here. So y then is equal to 13 divided by 2. we know is 6.5, so 130 divided by 2 has to be 65 degrees. I'm now going to put that on my diagram, so that's 65 degrees. Now, what other angle property can I use to find the other angle here, which I'm going to call Z? Based on our theorems, I can see here, if I visualize this chord, I have two triangles here. That means the angle in the same segment theorem applies here. This angle here from this triangle is 27 degrees. Therefore, Z will also be equal to 27. And you can write angle in the same segment. Angles in the same segment are equal. So now that we've got those two angles, let me just put 27 here as well. And then I'm going to prove that angle at P is equal to 27 degrees plus 65 degrees. So I'm just going to quickly put that in my calculator, and then we'll see that it's not 90 degrees because that's what we're trying to prove. So therefore, 27 plus 65 gets us to 92. So the angle at P is 92 degrees. Therefore, we know 92 is not equal to 90. So we know that QS is not a diameter. So we end intelligently by telling our examiner that we've proven it is not a diameter. And there we go. That's another 4 marks there. So now we're going to do another question, which is our final question, and then we are going to summarize this lesson. Here we're told that A, B, and C are 3 points on the circumference of a circle with center O. So clearly we know that O here is the center because we were told. B, D, and C, D are tangents to the circle, which we have reviewed when we were just beginning this lesson about the equality of tangents. And A, B, C, D is a kite. Angle BDC is equal to X. We can see that on our diagram. We're asked to prove that angle ABO, so let's identify that, ABO, we're proving that this angle here is equal to 45 degrees, take away X divided by 4. So, breakthrough to this question, clear step-by-step ways. We know that the angle here is 90 degrees at B, and the angle here is also 90 degrees, which means then if I look at this angle here, it is going to be equal to 180 take away X, since this angle here plus X should be equal to 180 as well. So I'm going to call this angle BOC, and that's equal to 180 take away X, which is the angle here. So that's my first step. Now I'm going to put that on my diagram. So this is 180 take away X. I can see here, based on the theorems I've done before, that angle BAC, which is this angle here, the angle at the center we know is twice the angle at the circumference. So therefore, this one is going to be half of the one we just found. So I'm going to write angle BAC is equal to then 180 take away X divided by 2. Very important there. So I'm just going to write a half of 180 is 90, and we can just write a half minus a half X, which we can write as minus X over 2. And I would suggest that you put it that way so it's easier to see. Now I'm going to write this here on my diagram as well. So that's 90 minus X halves. Okay, further on our way. Now we remember we're trying to find the angle at B. So what we're going to find now is this angle here. We're going to find the angle here at O. And we can find that because angles around a point add to 360 degrees. So if we do 360, take away, again, put in bracket what you're subtracting, 180 minus x. Then we'll see that when we expand the bracket, what the true answer is. So we got 360, negative times 180 is negative 180, and negative times negative here is a positive x. Simplifying that, we get 180 take away from 360 is 180 plus x would be the angle here. So I'm just going to write that here, 180 take away, plus x. So now I have enough information for me to find the angle I was asked to find, because I know two angles in this quadrilateral and I know the angles in a quadrilateral are to 360 degrees. So what I'm going to do is to add the two angles I already have, and then I need to subtract that from 360 and then divide the answer by 2, since the angle at C here will also be equal to the one I was asked to find. So what we're going to do, we're going to add 180 plus x, and we're going to add that to 90 minus x halves. Okay, so 180 plus 90 is 270 degrees, and we've got a positive x, which is 1, take away a half, which is going to give us positive half x, which we can just write as x over 2. So we know the sum of those two. We now need to subtract that from 360 and then divide that by 2. So we're going to go 360 degrees, take away, remember what we're subtracting, we put that in bracket. So that's going to be 360 take away 270 plus a half x. And then when we're finished, we're going to divide that by 2. So let me just put division by 2 here, because it's really easy to forget things like these. So it's best to write it first and then come back to deal with it after. So we need to expand our bracket here. So 360, and negative times 270 is negative 270. And negative times positive a half here is minus x over 2. Subtracting here, we get 360 take away 270 is 90. So remember, we need to divide that by 2. So I'm just going to write it here. So that's 90. And then we had minus half x. We now need to divide this by 2, which is the same as multiplying by a half. So what I'm going to do, I'm just going to do a half outside the bracket, and then I'm going to expand. So a half times 90, half means 90 divided by 2 is 45. And then 1 times by minus x is minus x, and 2 times 2 here is 4. And so then, after all of that, we have now proven that the angle there is equal to 45 degrees take away x quarters. Very good. And I would suggest you go back through these questions. These questions have a way to repeat on your exam. The only thing that can happen sometimes is that they may change the size of the angle that you've got, but the principle will still be the same. So there we have it. Lovely 4 marks there. I hope that you have managed to get to the answer. And what I would suggest as well is that you write the question down separately, put away your working out, and try to do it again a few times by yourself, so that clear logical thought stays with you. Well done for getting to the end of our Circle Theorem series, and well done for accessing as well those proof questions. So now it's time for our key takeaways. So what I'm going to do, since I've already summarized in part 1 and 2 the theorems that we were exploring then, I'll just summarize here first of all the 3 that we looked at today, and then give you a very good practice that you can use to remember all your theorem using acronyms again. So the theorem we looked at first today, the new one, was alternate segment theorem. The second one we looked at was the angle in the same segment are equal. And the final one we looked at was the perpendicular from the center passing through and intersecting with the diameter will always make a 90-degree angle. Now, I know that at this point you may be saying, there are so many theorems to remember. So now I'm going to give you something that you will thank me for. So here is what you could use to remind you of all those theorems. All the smart cats beat the stupid rats. So each letter is for one of the theorems. So A, alternate segment. T is for the tangent theorem. S is for the semicircle. C is for the cyclic quadrilateral. B is the perpendicular bisector, so B is for bisect. T, twice, so angle at the center, twice the one on the circumference. S is for the segment, so angle in the same segment are equal. And then R is that the radius and the tangent. R is for radius, so radius and a tangent meet at 90 degrees. So all the smart cats beat the stupid rats, just like you're going to beat these questions when you see them in your exam. Now, in summarizing, finally, I'll say, please remember, if you haven't yet, subscribe, share, hit the notification bell, and help other students as well to get the chance to benefit from these beautiful lessons. What can I say? You have done 3 lessons on circle theorems. Thank you so much for watching.